Hi, Dr. Zhang. This is Matthew Kahn in ECE5701 Distance Learning, here to present to you my Project 2 code and simulations. So I'll start with the code changes I made and then show you the simulations. And the first change I made to the code was to add the mapping tables for 16 QAM and 64 QAM using constellation values from -3 to +3 for 16 and -7 to +7 for 64. And then the next change I made was to include m as part of the equation for the int sim random value generator, which is used to index the mapping table to generate the random symbols. And I also updated the sigma calculation based on the average amplitude for 16 QAM in this case, which I found was the square root of 8.97. So inside the square root for the sigma calculation I have 8.97. I also have m equals 16 right now for the 16 QAM simulation. After that, I included cases for the 16 and 64 QAM to index the mapping table with a random symbol generator. And then I added cases for demodulating the 16 and 64 QAM. And I did that by taking the absolute value of the difference between the transmitted signal, or the noisy signal, and the original signal. And if that's greater than 1, I incremented the error count. And I did not change the BER calculation. So it still counts one symbol or one bit error if it sees a symbol error. So this does not take into account the case where there may be an error throwing the symbol off by more than one constellation distance, in which case you would have more than one bit error for a single symbol error. But that's a pretty uncommon case, so this should be pretty accurate. And then I just included all the graphs. And so I'll move on to the simulation for 16 QAM here. So it's running. We get a number of errors equal to about 2,500. So sometimes the boundaries come out funny for this, but it looks correct. This is the demodulation table, and we see clouds around -1, +1, 3, and -3. And so that looks about like it should. There's some overlap as expected with 16 QAM because it's more susceptible to noise than QPSK. And the wireless channel mapping looks as expected, rather cloudy for a higher order QAM. And the channel impulse response follows as expected the Rayleigh distribution, and if it looks to me like the integral of this curve, or the sum of the values, is equal to 1 as expected. And finally the BER simulated is just about equal to the theoretical BER. So that verifies my calculation for sigma using the average amplitude for the constellations. So that was 16 QAM. I'll switch this to 64 QAM. Just change m here to 64, and I'll change the sigma calculation to be based on the average distance to a 64 QAM constellation, which I calculated to be the square root of 37.05. So I've put 37.05 inside the square root for the sigma calculation. And I will run that. And you should expect to see a higher error count here. I'm expecting over 2,000. And so we see about 24,000. Yeah, I meant over 20,000. So we see about 24,000 here. And so again, we see an even cloudier demodulation table, but you can tell it ranges from -7 to +7 and looks about like we would expect. There's a bunch of overlap, which gives us a high error rate. And the channel impulse response follows roughly a Rayleigh distribution, and again looks like it sums up to 1. And the simulated BER is just about equal to the theoretical BER, and so that again verifies my calculation for the average amplitude for a constellation using 64 QAM mapping table. And one thing I wanted to point out with this was that I noticed a difference when I included this little bit of code that I have for the demodulation, which accounts for the situation when a demodulated symbol is noisy to the point that it's demodulated outside of the mapping table by more than 1. So say we had a transmitted symbol of 1 plus j times 7, which got so noisy that it was demodulated to 1 plus j times 9. Normally that would cause an error, but in reality it's still closest to its originally transmitted symbol, so it could be demodulated to the correct symbol. So this code here accounts for that, and we should see, when I add this code back in, we should see a lower actual BER compared to the theoretical BER. And we see the error rate is dropped by about 3,000. So that confirms that many of the errors are being counted when symbols are thrown outside of the mapping table, but still closest to the originally intended symbol. And so we see that the actual BER is noticeably less than the theoretical BER. And you can see in my report my calculations for the average amplitude, as well as the code snippet I used to account for those symbols that were demodulated to outside the mapping table, as well as other simulation results. And that's it. Thank you, Dr. Zhang.